amount of ISI as we proceed is a disaster. This will blow away the communication system. Basically, you might as well flip coins and forget about even taking the channel output if you're going to run through a symbol by symbol detector with this kind of ISI. So we're going to have to do better than that. Okay, so that's our model. So we're set up for modeling systems. We can get this Q of t. We know what the ISI looks like. We don't know what to do about it yet. That's coming in subsequent lectures. We have an idea what ISI is, how to model it. I'm using Q. It's not the Q function. This Q is I thought I could reuse Q again because it's so much different than the Q function that you wouldn't be confusing this in context. This one's characterizing ISI. You would not be sticking signal to noise ratios inside for the Z transform variable D and confusing that way. Hopefully not. Somebody smiled in the back saying, I think you were thinking, yeah, I probably will, but please don't do that. We've reused Q for this. What I'd like to do is now, also in setting up our voyage into intersymbol interference, is return to the correlated Gaussian noise, which is section 1.7 in chapter 1. And what happens there is I have a signal x of t that doesn't have the filtering. Remember, we didn't have any filtering issues in chapter 1. But I had some noise added to it that was Gaussian. Let's call it some, I don't know, n tilde of t. And we'll say it has kind of n naught over 2 involved, but it's got some shaping also. So its power spectral density is n naught over 2 times some function s. I'll call it s sub n of f, if you will. So it's kind of a normalized power spectral density where I've normalized, I've divided out n naught over 2. And we'll call this output, let's say, here, y tilde of t. All right. Well, I submit that that is an intersymbol interference channel, even with no filtering in the channel. And it's there in disguise. How do I get there? I take y tilde of t, and I whiten the noise. Well, I can do that essentially by dividing by 1 over the square root of Sn of f. If I can design a filter, and if Sn of f is a real autocorrelation function, I can always design such a filter, okay, and it can be realizable and causal and such. As a whole theory called Paley-Wiener theory that can be used to implement filters like this. I cover it in the notes, but it's not particularly important here. You get the basic idea, divide by square root of Sn of f, and I'm going to get flat for the power spectral density on the output. Because remember, we take the PSD of the input, multiply by the magnitude squared of the channel response, or the filter response in this case, and we get the PSD on the output. So I'm going to divide by 1 over Sn of f, the PSD of the input. That's going to leave me with n out of 2, the output. I call this output y of t. Okay? And this is a noise whitening filter. So if I see colored noise, first step is to whiten it. Let's call this filter here g of t, however we chose to implement it. Then I would have an equivalent channel. From x to y of t, the output of this noise whitening filter, and it's going to look like this. X of t passes through g of t, and now I have additive white Gaussian noise, n naught over 2, and y of t, right? Because I know the noise at the output of this filter is now white. It's got variance n naught over 2 per dimension. And I've got this linear filter here, g of t. Now, its origin is not the same as the channel filtering itself. It has nothing to do with the basis function. It has nothing to do with the channel impulse response. It's an artificial part of the channel that I have, in fact, added myself because I have whitened the noise somewhere in my receiving structure. But if I call the output of that y of t and I set it up, and if this transformation is 1 to 1, by the reversibility theorem in chapter 1, I haven't lost anything. And so I'm exactly back to the situation that we just modeled, which is intersymbol interference. Okay? The intersymbol interference is characterized by G of t. So you can kind of look at noise and pretend it's intersymbol interference as a channel. You actually get some intuition. Take the noise and invert the Fourier transform. And look at that. That's kind of like a channel. That's telling you equivalent effects. If I had notches in a channel, okay, which are caused maybe by that multipath fading we're talking about, that's going to be the same as if I had very narrow band noise, like some kind of sinusoidal interference at some frequency. They're going to produce similar degrading effects on a channel. So you can get intuition. You know about ISI, you know about noise. You can kind of use this and go back and forth between the two. Now, if I have both, no problem. Band limited channel. Also, then what I'm going to have is x of t now proceeds through filter h of t. It's got correlated additive Gaussian noise added to it, which is n naught over 2 Sn of f, produces an output, let's say y tilde of t again. Then clearly I can still run through the whitening filter, and now what my channel looks like, the equivalent channel in this case, is x of t running through h of t convolved with g of t, or h times g if you will, with additive white Gaussian noise and an output y of t. And so now this is the impulse response of the channel. And if I know the basis function, then my p of t in this case would be phi of t convolved with h of t convolved with g of t. And I have p, then I can go to q of t, and I can characterize that channel in terms of intersymbol interference. Okay? So the trick in dealing with correlated noise is simply to run it through a whitening filter, and we can treat it like ISI. So now we've set up a fairly powerful theory, okay, at least in terms of modeling things, where we've got this complex signal. So we've got PAM, QAM, QPSK, all on the same terminology. Okay, we can handle correlated Gaussian noise as well as white Gaussian noise. We just have to put this whitening filter in, and we've got a model for all of these different types of modulation techniques, and basically any type of linear channel and any type of correlated noise. And now we're going to begin to develop a theory of what to do if I have a symbol by symbol detector, which is the easy type of detector that's in predominant use in terms of a receiver theory. And we're going to go through this function q of t, which is then going to allow us to develop, well, a theory of what kind of receivers work well, how do we set up their parameters, and how close are they to the matched filter bound. Are they doing well, or are they not doing so well? If they're not doing so well, we're going to have to go to a more powerful technique if we really need the performance on the channel. Okay? Any questions? Yes, sir.
So you went through this trick to convert the colored noise into ISI, but we could go the other way. Why is it preferable to analyze it as a ISI rather than analyzing a channel that's clean except for colored noise?
Well, if the noise is colored, then, well, there are two answers to this. One would have to do if I had the optimum detector theory. If the noise is correlated, then that detector theory we had of picking the closest point and such in chapter 1 no longer applies. Okay, so the rules, the maximum likelihood rules, are going to be warped, and that is not true in the case where we're still going to do a symbol by symbol detector. I only have to look at the power of the noise. And in effect, what you said in that second case, that second answer, is what I'm doing with the distortion signal, except I'm including both the effects of noise and the ISI in two components. But in effect, E sub k is the noise signal that you just described. So we are doing that. We're doing both at the same time. Okay, any other questions? I'm going to let everyone go a few minutes early here, but if you're interested in the tape ahead, it'll be in 15 minutes in the Skilling auditorium.